In this tutorial/demo, we're going to show you how to build a very simple model in RAS2025, and that serves two purposes. This is actually a workshop that we do early on the first day of our RAS2025 class, because at that point in the class, it's time for you to build a simple model. So if you're working through those class materials, congratulations, it's time to build a model. But it also is a demo for kind of the simplest way to build a quick model in RAS2025. The core is turning to what we call the rapid planning process. And in the rapid planning process, the whole idea is to get to very simple answers as quickly as you can in the scoping process with a model that you could later refine to get better answers. And so we want to use this model as a demonstration of how quickly you can get to some sort of scoping level answer with a new hydraulic model using existing data that are on the web. There's a link to the workshop in the video notes, but if you go down to building a simple model, that's what we're going to be working on. And all the files you need are right here. We've got the terrain, the flow data, and a little GIS data that you're going to be working with. All right, so we are going to just create a new project, and let's just call it a rapid demo. Okay, the first thing we need is a projection, because everything we do in RAS now is geospatial. And so I could get that for my terrain if I wanted to, but I also have a GIS layer here which has a projection file. So we'll kind of run old school and just bring this PRJ file over. We'll drag it in here, and you'll see that updates the projection we create, and we're good to go. Okay, so the first thing we need is a terrain. So I'm going to come over here to the terrain node of the tree, and I'm going to create a terrain. And there's a couple of ways we could do this. We have a terrain. You might have existing data, so we can come in here and import the terrain file. And we navigate to the terrain and open it. And we're ready to go. And incidentally, this is Yosemite, one of the natural wonders of the world, one of my family's favorite places. We're going to just make a model of the Merced River as it flows through Yosemite. Incidentally, my colleague Cameron Ackerman made this workshop. The other thing you could do is you could come in here and make a terrain, and you could use the USGS importer. And in that case, you query the area. And because this is a US system, you have direct access to any of the terrain data that the USGS has, and we can just download that and bring that in. But we do that in a different workshop. We just want to make sure we're showing you all the ways you can use existing data. Okay, so we have a terrain. Next thing we need is some sort of spatial description of the roughness. Now, we'll go in here to surface layers. And if you're making a more detailed model, you can bring in classifications. It's actually pretty easy to bring in classifications automatically if you're in the US, but we're trying to make the simplest possible model we can. So we're just going to start with an n value layer, and we're just going to have a constant n value anywhere. You could go to a classification layer, but keeping it simple, this is a mountain river, gravel bed. So let's say 0.05, and now we have a constant n value. I'll turn that off so it doesn't override everything. Okay, so now we've kind of done the simplest possible spatial representation of the landform. What about channel? What about bathymetry? Well, this river actually doesn't have bathymetry data, and usually that's a big no-no, but this is a mountain gravel bed river, and so if you fly your LiDAR at low flow, really all you're missing are the pools, so it's actually going to be good enough for flood risk management. You wouldn't do this with, say, the Missouri River or a deep sandbed river where you absolutely need to go in and cut the channels. We'll do other videos on how to work with that. Okay, so the next thing we need is a geometry file. So we will come over here and choose geometry, and you'll notice that previous versions of RAS, you had to go to a separate editor to define your terrain and n value layers. Here you just select them associated with your geometry. We have these two terrain layers, but we choose the one we want and we create. And then, we have a lot of content up about how to create your mesh, but meshing has become much easier. And we're going to make the simplest possible mesh. And to do that, we draw the conceptual mesh. For this, think about the old perimeter, although it's much more powerful than that. You can do so many more things with the conceptual mesh that we'll show in other videos. But here we just want to show you the simplest possible way to build a model. So we're going to select the conceptual mesh, select the edit tool. There's no kind of turn on or turn off editing in RAS anymore. If you select the edit tool, you're going to edit. And then we will draw our perimeter around our possible flooding area. There's much more detailed ways to do this, but we're trying to build the fastest possible model. All right, and once RAS sees that it has enclosed an area, we get a region. Once we have a region, we can make a mesh. So we come in here, and how big should our cells be? Well, I have no idea. Let's guess. Let's say 5,000 feet. Well, that's what a 5,000 foot cell looks like. That's too big. Let's say 10 feet. Well, that's what a 10-foot cell looks like. That's too small. And so we can go in and let's say 500. What does 500 look like? That's a pretty good size cell. Let's generate the mesh. I really like that mesh for a first cut expedited analysis, but we can go in and now click on the mesh and see that's less than 600 cells. That's not going to kill our runtime. And so what if we go in and say, actually, I'm trying to make the simplest model I can, but we can definitely get away with 200 even with a simplified model. And we regenerate cells. That'll give us about 3,500 cells. Well, that's pretty good. Let's do that. Okay, so we have our geometry. What we need next is our flows, our boundary condition. So we'll come in here to the boundary condition. And this is a little bit different. You actually have to give your boundary condition a time window from the beginning. There are reasons for that we'll go into in other videos, but you don't actually have to use this time series. This is just the time window of the flows that you're putting into this boundary condition. And so we're going to start at the 1st of January 1997. And we'll let it go for 5 days until noon. So the 5th of January, and we'll make it 1200 hours. And create. Okay, so now we have a boundary condition. The next thing we need to do is we need to define the boundary condition lines. Where does the boundary condition come into the model spatially? Now this is a little bit different because this used to be in the geometry, which actually was a huge hassle. So now if I select boundary condition line and go up to the edit tool, I can zoom in to my boundary condition, and I'm going to go from left to right. So I'm just going to double click here and double click there, and I now have a boundary condition line. And so I come in here to define it. I can change the name. We'll call that upstream. The Merced River flows to the left. And now I can add data to it. The nice thing is you could add actually multiple boundary conditions. When we have constituents, you could put sediment in here. We're just going to add a flow series. So we'll say hydraulic data, hydraulic flow tabular. That's exactly what I want. And so we'll create that, and then I'll come over here and select it. So now let's go get those flows. So I'll come back to my data and I'll open my flow data, and you'll see we have a hydrograph and it is 15-minute data. So I'm just going to come in here and copy those. It's about 430. But the thing you can see here that here we have hourly data. We want to definitely change that. So we're going to change this to minutes and make it 15. And then you can see that now we have these 15-minute increments. I'm just going to go in here and say Control V. I use Control C to copy. And now if I go to the plot, we can see our hydrograph. Okay, so we have an upstream boundary condition. Let's go define our downstream boundary condition. So I'm going to go to the downstream end of my model. I will come in here, and again, we want to create another boundary condition line. I'm going to double click. Let's just call this downstream. And here we're going to use everyone's favorite downstream boundary condition, normal depth. Now, all normal depth does is it uses the Manning's equation to determine what the stage is downstream based on the flow, based on the flux. And to do that, we need a friction slope. And so we know the friction slope here. It's 0.001. Again, this is a moderately high gradient stream, even though it's through a valley. This is not the lowest uncertainty way to define your boundary condition. So if you do this, you want to move your boundary condition downstream a little bit from your area of interest to allow the equations to self-correct before the hydraulic results get to your area of interest. All right, so now we have our geometry, we have our flow, and just like kind of old school RAS, now the next thing we need is a plan. And so we'll come in here to this plan node on the tree, and we'll ask for a plan. And now everything's already set up for us. We didn't give our geometry or boundary conditions special names, but you can choose if you have multiple here. And then we just kind of adopt the time window of our boundary condition. We could say, hey, I want to make this custom, and I actually only want to run a day and a half of that, and that would work out just fine. But we're going to actually run the whole time window. And so we'll create this plan. And then when we select the plan, you see you get lots of like plan effects. Now we'll go into all of this. This is using the shallow water flow equation with CPU. And then there are a lot of advanced features as well. And we'll talk about all of those in the other class videos. But the main thing I want to do here, we're trying to run this model as fast as possible. We're trying to do our simplest possible model. So we will go to diffusion wave. The time step we're not as worried about because for now, RAS2025 is an explicit model, so we're going to compute the stable time step for you. And so then I'm going to come up here and press compute. It'll send me into my compute window. We'll do a little pre-processing. And then these tools are pretty cool. The bottom one shows you what percent of the model, what percent of your cells are wet. And so you can see as we flood, we get more wet cells, which actually drives your runtime because the more wet cells you have, the more computation we're doing. And then up in this little diagnostic, it shows you what time step it's using. So you can see that it was running 1 minute to 30 second and then kind of stabilized for the flood portion around 20-second time steps for this run. All right, so now we go back to the map because that's where most of these things happen. And you'll see we now have a new thing in our tree called results. If I go and I turn that on, you'll see we have latest. As you do more runs, you'll actually get like a history of results there. And if you select this, you see you get your time bar up here. And by default, the result is depth. But you can come in here and you can switch that. You can switch it to velocity. You can switch it to water surface. But let's go to depth. And so now we can see our inundated area. If you're interested in time series, if you're interested in like arrival time, you can right click on any of these cells or cell faces and query a time series result, and we will interpolate a time series for you in real time. Now this is a water surface result. It used to be that you had to kind of go to the tree and click on the result you want. But now if you ask for a result in a particular place, we'll give you all the results. You can switch from water surface to depth to velocity, all kind of on the same plot. And then the other thing that the model asks you to do is to digitize a profile line down the middle so you can look at results. And so let's do this for a portion of the plot so you guys don't have to watch me digitize for a minute and a half, but we'll do something like this. And again, with everything that we do, when we start digitizing, we double click, and then I'll kind of follow the center line of the channel here for a little ways. And then we can right click on that and we can plot a results profile, and we can get our classic longitudinal kind of a 1D result with the terrain that's underneath it. And so that's a very quick demo of how quickly you can get a model up and running in RAS2025. Of course, I would go in and refine it with a couple of more break lines. I would probably put another 6 to 8 minutes of work into this model before I turn it over to the planning team. But you can see that we're still like under an hour to get answers that can be useful for early level scoping and decision making. I'm Stanford Gibson, the sediment transport specialist on the RAS team. This model and this workshop were developed by Cam Ackerman, one of the senior modelers here on the RAS team, and this video was funded by the HEC-RAS program.